You're going to build a stone wall. The wall should be straight and n meters long, and its thickness should be constant. Okay. The wall should be straight n meters long. N meters long. The wall should be n meters long in width, I guess, and in width. Thickness should be constant. However, it should have different heights in different places. I see. So n in width, different heights in different places. The height of the wall is specified by an array h of n positive integers. Hi is the height of the wall from I to I plus 1 meters to the right of its left end. Okay, so that just represents a wall. In particular, h0 is the height of the wall's left end. If and h n minus 1 is the height of the wall's right end. The wall should be built of cuboid stone blocks. That is, all sizes such blocks are rectangular. Your task is to compute the minimum number of blocks needed to build a wall. Okay, so one sentence summary. Compute the minimum number of blocks needed to build a wall. The wall in H. Specified by H. So what is blocks here? I don't really know what blocks is. The wall should be built of cuboid stone blocks. Alright, let's look at an example, maybe that clears things off. Given an array h of n positive integers, specifying the height of returns the minimum number of blocks needed to build it. For example, given array h containing n equals 9 integers. I'm going to write this down. It helps me if I draw the wall, I think. Oh, okay. They even give you a demonstration, a visualization here. But h0 is 8. h1 is 8. So 8, 8, 5, 7, 9, 8, 7, 4, 8. 7, 4, 8. Okay, so these are the walls, heights of the walls. So I'm assuming this is 8, and then this is 8. This is 5, and then 7. 5, 7, 9. 7. Wait, I thought... Height 2 is 5. What the hell? Five, 7. I'm assuming this is 7. 5, 7, 9, 8. So this one's 8. This was 8. Wait. We have 8 and then 4. So this is 9. This is 9 right here. 8 right here. And then 4 right here. Eight, 8. 7, 6, 5. 3, 2, 1. 8, 8, 5. 8, 8, 5. And then 8, 8, 5, 8. Wait, 8858. No, 8857. Oh, this is confusing. 8857. So I'm assuming there's like 2 blocks of 8, 7, and then 9, 1 block of 9. 5 is 8, another 8. And then 7 is another 8. It's another 8. Or no, that's a 7. That's a 7. Okay. And then 4. 4. And then 8 again. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Wow. So what I did, I just used like rectangles to describe the heights, but I guess 1, 2, 3, 4, 5, 6, 7, 8. If we just use like one rectangle for this one, write an efficient algorithm for following assumptions. Okay. So we're supposed to find the minimum number of walls needed to build to the heights. Okay, so what I noticed is if we have 2 consecutive heights, we can just use one cuboid to represent that, right? Some patterns. Use one cuboid to represent consecutive heights. Okay. So h2 equals 5. I think it's how we can build off of a previous block. Like for example, this block right here is representing both 8 from H3, or no, 7 from H3, and then 7 from H6, right? This one block is representing both of those. So whenever we have an equal number, I think we can use so for example, in H2, we also have 5, and later on, we don't have 5, but we have a 8 that can build off of this 5. We have 2 8s here. So how do we determine that we can reuse certain blocks? And another case is where we can use a previous used cuboid to build off to the current one. Let's use a lower height block. Leverage it to create one block that represents 2 heights. Like for this one, 7 and 7, H3 and H6. Both use a 7 block. Leveraging the function to return 7. So what is the we probably need a visualization in our heads, but two things. One, leverage older blocks to build new blocks. So the key is to using one block to represent more than one height. That's the key. How are we gonna do that? At a lower height, we need to know how many of the blocks can leverage and take advantage of the fact that they are lower. For example, this 5 has 8, 9, and 8. 8, 9, 8, 9, 8, 7. Okay, well, this looks like a stack problem because look, we see that, let's say the peak or whatever's most recently just inserted, we insert the used cuboid into the stack, and at every point that we iterate, let's say we are on 8, we peak C5 and say we only need 3 height and can build off of 5. So we do that. So what do we actually store in here? We store the height of the block we used. So wait, hold on. So the height of the block we used is gonna be 2. But I think it still should be 7 because 9 can also build off of 7. But 8 can't build off of 9. So we pop 9 from the stack, and when we pop 9, we get this guy as our peak. We can't actually use that. So we only need like 1 block here. And when I say leverage, like, I guess you can use that. And then the next one is 8, so you can use 1 block here. Next one is 7. 7 is less than 8, so we pop. 7 is less than 9, so we pop. But 7 is equal to 7, so we're going to use it. And we're going to push it into here. Right? We're going to push h3 equals 7. We can't leverage these anymore. No, we can't leverage them anymore. So we're going to pop those. It doesn't matter. Right? And we don't need to append another one in here because we've already used it. And these are gone now. 7 is also gone. So now we're looking at 4. We can't leverage it. We pop. Can we leverage 5? No. Pop. Nothing in the stack anymore. We can't leverage anything. So that's the end of this block. I like this idea. So let's come up with some rules and actually like try to implement this shit. We need a stack. Initialize a stack. And at each point, we're gonna look at a tower, or at each point of iteration of the H array, we need to store the height. No. We check if stack is not empty and peak. If there is an element, a height that is less than or equal to the current height, we will take it. We will take advantage. So for example, let's say we have 8. We have the 8 in our stack. Because the stack is empty, we just push it in there. And then we have 8 again. That means we peek at the stack. Notice that it's an 8. We can represent the 8 using the 8. So what we're going to do is we're not going to increase the number of blocks used. We only increase it when the block is greater than the leveraging one. If that's the case, we don't really need to pop anything. So for example, h2 is equal to 5. Can we actually leverage anything? We pop these two, no. It's fine if we don't append these two. We're never gonna use them again. We can't. So that's the algorithm. There are some cases here. If the blocks are equal, we don't increment num cuboids at all. If the block is less than the peak, oh no, if the block is less than the peak or that popped, we continually pop until stack is empty, or we find something less than or equal to our block. So if we don't find anything, if no found, increment block and push that height into the stack. If found and height is same, we don't increment height. If not found, if the height is too big, we just pop. If the height is smaller, can we guarantee that we won't find anything in the stack that's gonna do better? Yeah, no, we won't. We have already popped everything greater than that number in that stack. So whatever peak we're looking at is the maximum number at all times. Whatever peak we are looking at, if that is the maximum number. So the stack numbers, they don't get greater. They don't increase. So that's because, let's say there was 8 here, right? 8 is less than 9. We can't leverage it. So we're going to pop 9 anyways. I think that's a pattern that we got to realize that. I realized it. My dog is under my desk right now. I think she needs some attention right now. But I gotta lock in, so I'm very conflicted. If not found and height is smaller. If not found and height is smaller, then we just push that into the stack. Also, we push back the element. Well, okay, do we really need to pop it? Can't we just like peek it? Because there's three cases, right? If the peak is equal, we don't do anything. If the peak is greater, we pop it. And if the peak is smaller, then we don't do anything, we just append our bigger one. So I guess I won't pop until this case. We continually pop. So I think that's the solution I'm gonna go with. Maybe there's more efficient ways to do this, but this is the only solution I can think of right now. I think that's the most efficient one. It's pretty intuitive in my opinion. I mean, I guess that's why it's an easy problem. But yeah, I think I'm gonna try to do this one now. Alright, so we have our stack. At each point, decide if these three, decide if they're, okay, so for I in range, length h, do we need the indexes? I guess not, so I guess for h and h, for every single height, we need to check if the stack is empty or not. If not stack, what are we gonna do? We're just gonna append it to the stack. Else, there's our three conditions here. So every single point after the first one, we're gonna do, let's see, so we're gonna peak equals stack -1. Stack isn't always not empty here, so we're good. Or stack is always not empty here. Yeah. Alright, whatever. Peak is the previous value. So if there's three cases. If peak equals to h, then we don't do anything, right? We need num cuboids. So pass or like continue. Elif peak. If peak is greater than the block, we continually pop until stack is empty or we find something less than or equal to our block. While stack and or stack, wait, hold on. While stack, I guess we can just have a break statement. If stack -1, just the peak value. Okay, so peak is greater than h, right? Peak is greater than h. So like that is useless now. We don't need to peak. I think we can just popped equals stack dot pop. And we continue this until stack is empty or we find a popped value. If popped less than or equal less than our current value h, then what do we do? So we found like 5, right? We're looking at 7, we found 5. What do we do then? We increment the count and we append to the stack dot append h, and then we break. Elif popped equal h. We do not increment the cuboids. And we append the popped back up. So in this case, do we append it into the stack again? Like, do we need the 5? Yeah, I think we do. Stack dot append popped. else. So this is the case where, like, yeah, we just keep popping them. elif peak. So peak is greater than, or no, the current is greater than peak. We literally just do stack append peak for h, and then increment the num cuboids. Alright, these are a lot of conditions. I feel like we can, actually, this is not too bad. This is not too bad. Let me return here, return num cuboids, see what happens. Got 2. Okay, so something seriously wrong. Yeah, this one. So whenever you append something, else we look at the peak, it's 8. Peak is h, so we don't need to do anything. We continue. I feel like we don't even need this shit, right? Like, we can just do if. So we don't increment anything, so that's 1. h2 is 5, so that is, h is actually less than, h is less than, so h is less than peak. So what happens, you're going to iterate the stack here, pop the stack. We already know this will be greater. So we pop twice, and we break, and we don't do anything here, right? So we reached this case, I think. So if we print the stack here, I'm pretty sure it'll be empty. So we need to take care of that case. Yeah, it'll be empty. So we need to still like add 5 to the stack. Do we just continue? I think we just continue. We don't even break. We just continue. And then here we do stack.append h. Because we never reached that satisfactory element, we must append it. Oh wait, no, not continue. Like, how do I continue to the next for loop here? I guess we just break, and else elif popped. If popped is greater than h, we just keep popping. And if stack is if not stack, we do that. Okay, I think this is it. So in this case, we have popped everything. Oh no. Oh my god. Dog was whimpering. I could not let her whimper alone. Okay, so 5, 5, 7, 8, 5, 7, 4. Is that right? Yeah. 7. Where's 9? Where's... Where's 9? Stacks right here. 9 gets in there. Then 8 pops that 9. Am I missing a num cuboids increment here? Yeah, here, right here. Yeah, that should be it. Yep, there we go. Okay, so this solution looks... It's not visually appealing. I really don't like the conditions here. And... yeah, I mean... what else can we do? Right? Like, I don't see any code modification I can do to like make that better. So I guess this is it. Some test cases I could try. Some edge cases maybe. Alright, so efficient algorithm, n is an integer within 1 to 100,000. And there can be one element as well. So what if it's like 8? Just build a wall with 8. Just a single rectangle. And what are some edge cases here? I guess just like the equal length and like alternating maybe. So this would be 1, 2, 3, 4, 5, 6, because we can't build off of 9 every single time. 4, this would be, oh wait, maybe if we build 9 like this, 8 like this, and then 1, 2, 1, 2, 3, 4. Yeah, actually, my code was better than my fucking thinking. Yeah, we can do that. We can do that in 4. This one we can do it in 1. We can do it in 1. What else? Like 100 height. You can't have negative heights. You can have like 2 height, I guess. And then incremental. No, actually 2 and then 2 and then 100 and then 2 again and then another 4 and then 2. So this one, 100 has to be allocated. 2 can be a long rectangle, so that's 2 rectangles so far. 3 can be another one. 2 we don't have to use. 100 can be another one. 4 is, or 2 you don't have to use. 4 is 5, and then 2 is nothing. So 5 cuboids. That should be 5 cuboids. After that, I think I'm gonna submit. Yes, sir. All right, let's submit. Okay, at least I can do this one. Okay, I'm feeling pretty good about stacks now. That was a nice problem. That was a really nice problem. So, okay, at least I can do these in a relatively, like, easy... I didn't really have difficulty solving these. I just don't like how long my solution is, but it is what it is. Is there a way I can improve it? Probably. Do we even need that stack? Yeah, I think we do. Alright. Let's add this into our list of problems. Or I guess I can call it pattern recognition. Lead code. Alright, while this is running, I'm gonna do this. So this was stone wall. Did I? Yeah. This pattern name. What is the pattern name for this? Reusing heights. Reusing heights. Um, yes, sir. Let's fucking go, bro. Let's fucking go. Core transform. Core transform here is very similar to the idea of use a stack to repeatedly eliminate. It's the same idea. Use stack to repeatedly eliminate. Like find the minimum number using a stack. Core transform. I guess for this one, find a minimum value. Optimize wall building with the stack by pattern. Recognize that invariant is what stays true at every stack, at every iteration is if there's three cases. One, wall height equal to each other. Wall height. So I guess popped greater equal to current h. Popped greater than current h. Popped less than current h. These are true at every step. I think that's what invariant is for this one. Brute force. I don't even know what brute force this is. I guess a recursive solution. It's too slow. The complexity of that would be like at every step you take or not take. Every step take or not take. It's a 2 to the n complexity for brute force. I think if you can do it in a brute force way. Improvement, potential improvement. Maybe. Let's see. I think we can definitely simplify these conditions. Let me see if we can do that. Can we simplify it? So we can definitely simplify this. So that it's not an if else. So that I don't have to check if the stack is empty every time. But can the stack be empty at any given time? I don't think so. After the first one, so that's a potential improvement. Remove the stack check out of the array. And yeah, this if statement gotta go. It's very inefficient to check that every iteration. And let's see. Peak is -1. I think that's fine because we're using that every single condition here. If peak is equals to h, we don't do anything. That's fine. While stack popped equals stack dot pop. If popped is less than h, we do that. We can make this a function. This is exactly the same as, wait, actually, do we need to pop? Yeah, I think this is fine. Yeah, I think this is fine. Maybe we can do something with this because we both have like stack append break. We can just do this after. Yeah, it's very minimal, so I don't think that matters. This one's good too. Like if the stack is empty, we have to append and increment the cuboids. Luckily I had a test case where like this was important. But I can see a case where I would have missed that. And yeah, this was very lucky because I got very lucky because I had a case where like all of the existing one, like 8-8, would have been popped because of 5. And if that didn't happen here, I don't think I would have caught that on, and I don't think I would have gotten 100%. So that's a very lucky. I got very lucky with that. All right, well, anywho, I think that was an excellent problem to begin with. I think I'm gonna move on to the next one.